Okay. So let's first talk about what does the first derivative, okay, what does the first derivative tell us about the function itself, okay? So take a look at this graph over here. This is a function. It's a continuous function. There's no break, right? Okay. Now from A to B over here, let's look at the first derivative. So the first derivative corresponds to the slope of the tangent. So I draw tangent line on those points between A and B. You see what kind of tangent line here is. Looks like they are increasing, right, from left to right, okay? So when we know that when the line is rising from left to right, the slope will be positive. So the first derivative will be positive between this point and this point, A to B. So we have this positive, right? What do you see about the function? Is it increasing or decreasing? Well, it is going up, right, from A to B, so it is increasing. I'm going to use this symbol here for increasing, okay? Now what about from B to C? I draw the tangent line here. You see it is falling from left to right. So the slope of the tangent will be negative. And you see the function is decreasing, okay? So function is decreasing, going down, okay? From C to D, again, the slope for the tangent will be positive because it's rising from left to right. So positive. And you see the function, it is going up, it's increasing, okay? So this is just some observation. Actually, it is going to, it could be proven, okay? It's called the increasing decreasing test. So I abbreviate this as ID test, okay? So it says that if the first derivative is positive on that interval, then the function is increasing on that interval. If the first derivative is negative on that interval, then the function is decreasing on that interval. Okay, so we could prove this. Okay. Now let's look at this example. Let's try to find where this function is increasing, where this function is decreasing. Okay. So we have a polynomial function, number one. So I outline the step over here for you guys. Okay, let's find the domain for this function first, the first step, okay? So it's very important to first know what's the domain. So we're only concerned about within the domain, okay? So what's the domain for this polynomial function?
All real numbers.
All real numbers.
You got it, okay? So that is all real number, okay? Now, we differentiate because we try to find those critical number and we want to see when the derivative will be positive, when the derivative will be negative, right? So I'm going to differentiate. So differentiate this function. Everybody tell me, what should I get? Shout out your answer here, okay?
12x cubed.
12x cubed. Yeah, minus 12x squared minus 24x, right? Okay, good. And then you factor this, okay? Because we try to find the critical number, we will set that equal 0. So it's better that you factor this so we can solve, okay? So factor this, we take out the greatest common factor, which is going to be 12x. And then we have this inside the parenthesis. Inside this parenthesis, we use try error to factor, okay? Using try error factor, what do you get? You get x minus 2 times x plus 1 in here, right? And then here you have a 12x. So 12x times this, okay? Now, polynomial is never going to be, it's going to define for all real number. So it's not going to be undefined, okay? So the only critical number, those critical number you get will be from setting the first derivative equal to 0, okay? So I'm going to set this first OT here equal to 0. So we can find critical number. Setting this equal to 0, what does the x equal to?
0 to
2,
-1.
-1. Yes, we got it. 0 to -1. Okay. And those are critical number. They're in the domain. Okay. And now, okay, now I have this method different from the book. I use a table to organize it. The book just write paragraph after paragraph, and I think a table is better, easier, help you to visualize it. Okay, so in my table, I make it 3 rows. Okay, so one is for x, one is for the second, one is for the first OT, one is for the function itself. And you have the domain is from -infinity to infinity, and then you put those critical number in this 3 separate column. Okay, one here, one here, one here. Okay, so you have this 0. Small. You have this -1. You start from small to big. Okay, so -1, smallest, and then 0, and then 2. You put the 3 critical number over here, and make a separate column for each one of them. Okay, and now you will use those 3 critical number to divide the whole domain. Domain is from -infinity to infinity, so over here will be from -infinity to -1, open parenthesis. Okay, and then in between will be parenthesis -1, comma 0, and this one here will parenthesis 0, comma 2, and over here will be comma over here will be parenthesis 2, comma infinity. Okay, so you separate the whole interval, you separate the whole domain by this 3 critical number here. Okay, because they're trying to ask you when the function will be continuous, or they're trying to ask you, they're asking you when the function will be increasing or decreasing, right? So if we put it down this way, and you will see that in the table. Okay. Okay. Now the first OT over here is equal to 0. Here, here, and here. Okay. Now we want to test the sign for the first OT, because when the first OT is positive, is increasing, negative is decreasing, right? So let's test the sign. I think it's easier to test over here. So let's pick a number. Okay. Actually, let's test over here. Okay. Okay. So we try to find the sign of the first OT on each interval. Okay. So we pick a number in that interval, in each interval. Okay. For example, in this interval, -infinity to -1, I pick -2. So I pick -2 in this interval. And I substitute -2 into the first OT. I see that this is negative, and this is negative, and this factor is negative. Negative times negative, it is what? Negative, right? Okay, so that is negative. Okay, so you get negative for the first OT on that interval. So I enter negative over here. Okay, now what about this on this interval? Substitute number. What number would you like to try? You can try -1/2, right? Try -1/2. Substitute into x. So it will be negative, and this one will be what? Negative. And then this one here will be what?
Positive.
Positive. Negative times positive give me positive, right? So we'll have a positive first OT here. So positive. And similarly, you pick a number here, say 1, substitute into x over here, and you'll get negative. Okay, and substitute a number in this interval, say 3. Let's pick 3 and substitute 3, 3, 3 here. And you see the sign, it is positive for the first OT. You kind of see there's a pattern, right? It looks like they alternate right here, right? Negative, positive, negative, positive. Notice that this is a case when you have the first OT, when you have this expression here, that each factor here is going to be linear. So x to the first power, x minus 2 to the first power, x plus 1 to the first power. So when they are linear, when each factor here are linear, the sign is going to alternate like this. Okay, so negative here, positive, negative, positive. Okay, I think sometimes it might be easier to test this one first, and then if each factor over here are linear, then you will alternate them, negative, positive, negative. Okay, now once we know the first derivative, the increasing decreasing test says that if the first derivative is negative, the function is increasing or decreasing. What does it say? First derivative is negative, then the function it is decreasing, right? So decreasing. And when first derivative is positive, function is increasing. First derivative is negative, decreasing. First derivative positive, function is increasing. So I draw this symbol like this for increasing, decreasing. Now over here, look at this function. Okay, you substitute -1 into the function into x, then you can find f of x. And I substitute -1 into x. I found f of x is equal to 0. And substitute 0 into x. And substitute 2 into x. I found the corresponding function value. This is 5 and this is -27. Okay. Now, in this table, that already answer the question. When the function, they ask when the function will be increasing and when the function will be decreasing, right? So instead of like the book, writing sentence after sentence, this table already answered that for you. The function is decreasing on this interval and this interval, decreasing here and here. This interval union this interval, the function will be decreasing. The function is increasing on this interval and this interval. So increasing on this interval union this interval. So this table already answered the question. So you don't have to write down sentence after sentence. And also, number 2, they ask you for local max and local mean of the function. This table also answered that. Okay. So this table answered that local max and local mean. Now see, this function is decreasing on the left, increasing on the right. Okay. So this function value here, it is a local max or local mean?
Minimum.
Local minimum. Okay. So local mean. Increasing on the left, decreasing on the right. This is a local max. Okay.
Max.
Decreasing on the left, increasing on the right. Still, this is a local mean.
Minimum.
Yeah. So local mean. So this table answers both questions, all the questions. Okay. And instead of writing a long paragraph, then this table organizes everything. Okay. So this is the way that I do it. Okay. Okay. Question about this?
How did you get 0, 5, and -27 again?
Oh, okay. Let me go over that. So over here, you have 0, right? How do you get this 5? Okay. So this is f of 0. Okay. So that was the function itself. So to find f of 0, you just substitute 0 into x. So f of 0 will be equal to 5, equal to this 5 over here.
Yes, thank you.
Okay. And f of 2 will be similar. Okay, any other question? What we have gone over, it is called the first derivative test. Okay, so let me review the step with you. The first derivative test over here is we will first get the domain for the function, and then after that you take the first derivative and then to find critical number. And then the third step, we try to organize user table. So 3 rows. x here, f prime here, f here. You use those critical number to separate the domain into disjoint interval, different interval. And then after that, you test the sign for the first derivative on each interval. If the derivative is positive, then the function is increasing. If the derivative is negative, the function is decreasing. Then after that, you can, based on those information, you can find local max and local mean, and you can find the interval of decreasing and increasing. They're all organized in the table. So that's called the first derivative test. Yeah, the first derivative test is actually a consequence of the increasing decreasing test. The book asks you to try to visualize it by using this diagram. Okay, so they say if first derivative is positive on the left and negative on the right, then this function value is the local max. If the first derivative is negative on the left, positive on the right, then this function value is the local mean, etc. For me, I don't need to memorize this. I don't need to, because the table here make it very clear, right? So you actually can see that's a local mean, and this is a local max. And make it clear. So I don't even need to worry about that. And over here, if the first derivative is positive on the left and also positive on the right, then what happens? F of C over here is neither local max nor local mean, right? It's not a local max and not a local mean, the function value at this point, because you see he keep on increasing here, right? So it's not a neither, okay, neither local max and nor local mean. Similarly, if the first derivative is negative on both sides, then FC here is neither local max nor a local mean. Okay, because keep on decreasing like this. Now the next example, example 3. Find the local max and mean of the function. Okay, so how do we do that? They give you this function. They also give you this interval. So this interval will be the domain now for this function. Okay, it's because this is given. Okay, so the domain over here will be from 0 to 2 pi. Because the equal sign over here, so that's a closed interval. Okay, bracket here and bracket here. And then the second step is to differentiate the function. So let's differentiate this. What's the derivative of this function? Everyone?
1 plus 2 cosine x.
Yes, 1 plus 2 cosine x. Okay. Now, to find the critical number, we're going to set this first derivative equal to 0. Now, remember, cosine x is defined for all x. So this is never going to be undefined. So the critical number can only come from when you set the first derivative equal to 0. Okay? So we set the first derivative equal to 0 to find critical number. So we get 1 plus 2 cosine x equal to 0. So cosine x will be equal to negative 1/2. Now remember, we're focusing on this domain that's given right now. Okay? 0 to 2 pi. So in this 0 to 2 pi, cosine x equal to negative 1/2. What does x equal to? Anyone? Look at this. X equal to
2 pi over 3.
2 pi over 3. Yeah, 2 pi over 3. You see, cosine is adjacent over hypotenuse. So depends on the x is positive and negative, right? X is positive on this 2 quadrant, so cosine is positive. X is negative at this 2 quadrant, so cosine will be negative at this 2 quadrant. So the angle will be at this 2 quadrant. But first, let's ignore the negative sign first. Cosine x equals 1/2. Then at the first quadrant, that corresponds to pi over 3, this angle. So the reference angle here will be pi over 3. So this reference angle, it is pi over 3. Then this angle here will be pi minus pi over 3. So that will be 2 pi over 3. So 2 pi over 3 is 1. Okay, this one. Now what about this one? Now because this is pi over 3, so this angle here will be pi plus this pi over 3. So that will be 4 pi over 3. So 4 pi over 3 is this one right here. So we get 2 critical numbers in this domain. critical number has to be in the domain. So we only concern about this two. Now, once you get the two critical number, you're going to put that in this table. Okay, let's put them over here and here. And then we use them to divide the whole domain. The domain is from 0 to 2 pi. So we also put the two endpoint over here. So this is the end. This is the endpoint right here. You put this endpoint over here. And then you put this critical number here. And then you put the critical number over here. Now it divides the domain into disjoint interval. So here will be 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, 4 pi over 3 to 2 pi. So you just fill in those intervals. Now, when x equal to this and this, the derivative will be equal to 0. So let's put that 0 over here and here. Now we want to test the sign. So let's try from 0 to 2 pi over 3. Let's pick a number. Let's try to pick pi over 2. Pi over 2 is between these two, these two ends. So I'm going to pick pi over 2 in this interval. Okay. So we have 1 plus 2 cosine of pi over 2. Cosine of pi over 2 is equal to 0. So 1 plus that will be positive. So we have positive over here. So that will be positive. The second one, from here to here, I'm going to pick pi. Pi is in here. So cosine of pi, it is -1. 1 plus 2 times -1 is negative. Okay, so that will be negative over here. And then from here to here, in this interval, we pick 3 pi over 2. 1 plus 2 cosine 3 pi over 2. Cosine 3 pi over 2, it is 0. So this result will be positive. So it will be positive. Oops. So that will be positive. Okay. Now once you test the sign, now what we have to do over here is to see increasing, decreasing, right? So increasing or decreasing here, the function. The function is what? First derivative is positive, increasing or decreasing?
Increasing.
Increasing. Okay. So increasing here. First derivative is negative, decreasing. First derivative is positive, the function is increasing. So I just use those symbol, okay, to indicate that. So this will answer the question when the function is increasing and when the function is decreasing. Okay, so you can see it in the table. Okay. Now what about this function value? Now some of you asked about how do you find this function value? I just substitute 2 pi over 3 into the f into the function. Okay, so and I got this. Okay, I found this. And I substitute 4 pi over 3 into x into the function, I got this. Okay, so that's how we got the function value. Okay, this is the function, so we substitute over here. This is a local max or local mean. Increasing
maximum.
Yes, increasing on the left, decreasing on the right, so that is a local max. And what about this? It's a local mean. Okay, so that's a local mean. So this table also answers the question, the local max and local mean. So I like it this way because the table, instead of the long paragraph, I like the table better. Okay. So yeah, that's how I do it when I was in China. Okay. Okay. So any question? Now I summarize the steps over here for you. The first derivative test. So step 1 is write down the domain. Okay, important because later on when we try to find critical number, the critical number has to be in the domain. Okay. Number 2, and you take the first derivative to find critical number. You set the first derivative equal to 0 or find out when the first derivative will be undefined, and then you find critical number. You find some number, but you have to check those numbers to see if they are in the domain. If they are in the domain, then yes. If they're not in the domain, then they're not critical number, and then you just discard them. Okay. Okay. And number 3, and use those critical number to divide the domain into separate interval, and you make a table. Okay. So that's the 3 steps. Question about that? First derivative test. Now that's the first derivative. First derivative tell you increasing, decreasing, right? First derivative tell you increasing, decreasing. What about second duality? What does the second duality tell you about the function itself? Okay, let's discover this. Looking at this curve and this curve, both of them are increasing, right? However, the way they bend is different. This one bended upward, right? And this one bended downward like this, okay? And this is called concave up, okay? This is called concave down. So bend it up and bend it down. The formal definition for concave up is this. So if the curve is always above all the tangent line over here, you see those pink tangent line? The curve is always above the tangent line, then this curve is called concave up. And you can just try to visualize it. It's curved up like this. So sometimes it could be like this, sometimes it could be like that or that. Like any part of this will be concave up, right? Okay. Concave down, the curve will be always lie below the tangent line. See those tangent line here? The curve always lie below that. So that's concave down. So bend down like this. And any part of this will also be concave down. So concave down, okay? So CU for concave up, CD for concave down. Okay, use that. Okay, look at this. So this is concave down, and here concave up. Here's concave down, concave up, concave up, concave down. Okay. Okay, now let's review the slope for tangent. So when you have a negative slope, okay, the graph will be decreasing like this, right? Okay. And when you have a positive slope, the graph will be increasing, okay? And vice versa. When the function is increasing, the first derivative will be positive, right? So when the slope of the tangent is positive, then the function is increasing, and vice versa. And when the line is horizontal, then the first derivative will be equal to 0. When you have a vertical line, it will be the derivative. What happened to the derivative when you have a vertical line? It is what? It is undefined.
Undefined.
And now we can make a snowman. Okay, you know how to make a snowman? Okay. So the snowman like this. So decreasing, negative slope. Increasing, positive slope. Horizontal, 0 slope. Vertical, undefined slope. Okay, so we can make a snowman. Okay, now let's investigate this. Okay, so over here we have this concave up curve. Okay, so over here you see the slope of the tangent, it is negative because falling from left to right. Okay, and here it is 0. The slope is 0. Here the slope is positive. See the first derivative over here, it is actually increasing, right? Negative and then 0, positive. First derivative is positive. First derivative is increasing, okay? And what happened to the second derivative? The second derivative over here is actually positive, okay? So positive. And it can reverse it, okay? Let's go the other way. When the second derivative is positive, then remember the increasing, decreasing test? Then the first derivative will be increasing because this is the derivative of this. So when this is positive, then this will be increasing. And when this is increasing, then you can try to imagine this. Then the graph will be concave up like this. Okay. Now, one way to remember is I make this diagram over here for you. Okay. So when the second derivative is positive, so I put positive twice, but that's for second derivative. Okay. And the curve will be concave up. So concave up. So I'll draw a smiley face, a mouth right here. The mouth open up. Okay, concave up like this. Okay. So the second derivative is positive. Then the graph is concave up. So we have a happy face. Similarly, when the second derivative it is negative, then we can find that the graph of the function is concave down. Okay, so we have a concave down. So when you are set and your eyes are closed and your mouth go down, right? So that's the set face. Okay, so that might help you to remember the relation between the second derivative and the graph of the function. Second derivative positive, concave up. Second derivative is negative, concave down. And that's called the concavity test. Okay, that's called the concavity test. Now let's try to use this example to understand this. Okay, so I would like to ask someone to read this, a volunteer to read this paragraph from here to here. Can I ask someone, can you read that to the class?
Sure. Figure 8 shows a population graph for Siberian honeybees raised in a apiary. How does the rate of population increase change over time? When is this rate highest? Over what intervals is P concave upward or concave downward?
Okay, very good. Okay, now here's the graph. Okay, it shows the population graph for Siberian honeybee. Okay, raised in a apiary. Apiary. Okay, I look up that the Chinese translation here. Okay, so over here you see the population. That's for the population, and this is for the day. Okay, so this is the population of bee. That okay. And the derivative of that corresponds to the rate of change of the population. Okay, remember that. Now you see that over here, this point. Okay, at this point over here, before that it is concave up or concave down. Before that, concave up or concave down.
Concave up.
Concave up, yeah. From here to here, concave up. Okay, and then from here afterward, concave down, right? Concave down over here. So over here, this point here, it changed concavity, right? From concave up to concave down. That we call this an inflection point. So we abbreviate that as IP. Okay, inflection point, IP. Okay, so it's not a VIP, it's IP. Okay, inflection point. Okay. Now, what does this say over here? Okay, when it's concave up over here. So the rate of increase of the first derivative of the population. Okay, let's see the rate of increase of the population. So you look at the first derivative. Before, the slope is kind of small, right? It's kind of close to zero. And then later on, it's going to increase, right? So the first derivative going to increase initially was, okay, I'm sorry. Okay, so the first derivative first was kind of small and then later on increased. So which means that the rate of change of the population first is kind of small, right? And then later on it get larger, okay? And then it's going to reach a maximum at this point, at 12 weeks. Oh, by the way, this is in weeks, not days, okay? At 12 weeks, then the first derivative is going to reach the maximum right here. Now afterward, if you draw the tangent line, you see the slope actually decrease, right? Steeper, less steep is almost horizontal now. Okay. Now after that, okay, the rate of change, the first derivative is going to decrease. Okay. So the rate of change decrease from week 12 to week 18 as the population begin to level off. See the population begin to level off here. Okay. And as the population reach its maximum value, okay, so looks like the maximum value that reach over here, it is like 75,000. And that's called the carrying capacity. Okay. And at that time, the rate of change over here, the slope of the tangent is going to approach 0. Hopefully, we're going to reach the inflection point of our pandemic right now. So the rate of increase is going to slow down, okay? And maybe hopefully level off, or maybe go down, hopefully. Okay, so inflection point is where the graph change concavity, from concave up to concave down, or concave down to concave up. So that's the definition for inflection point, okay? This is where the graph change concavity, concave up to concave down, or concave down to concave up, inflection point. So now we also have something called the, okay, that's a second derivative. Okay, so second derivative tell you the concavity. First derivative tell you increasing, decreasing. Second derivative tell you the concavity. Okay. Now, in this example, we asked to sketch a possible graph of a function that satisfies these three conditions. So, number one, we have first derivative is positive on negative infinity to 1, and then negative afterward. So we have positive here, negative here. So what happened to the function? Increasing or decreasing here? What do you think? Okay, I'm going to ask someone over here. Okay, Alex, are you here?
Yeah.
Okay, good. The function here is increasing or decreasing?
So increasing.
Increasing, yes. Increasing here and then decreasing here, right? First, they will tell you increasing, decreasing, okay? Now, and then over here, we also know the second derivative. Second derivative, it is positive over here, negative here, positive here. So the second condition, okay? Now, let's look at the concavity. Second derivative tell you the concavity. So I'm going to ask someone.
Hi, yeah.
Okay, so second derivative positive, the graph is concave up or concave down?
Concave up.
Yeah, concave up here, right? Concave up here, concave down here, concave up here. So second derivative is positive, then the graph is concave up. Second derivative is negative, concave down here. Okay? So I just use this symbol to indicate that. So I just to make it easy for me to indicate that. Okay? Now, and then we say that the limit of the function as x going to negative infinity is negative 2. Okay, so over here, so in the long run, when x go to negative infinity, you have this horizontal asymptote, y equal to negative 2. So that's the horizontal asymptote here. When x go to infinity, so on the other hand, the function value goes to 0. So this y equal to 0, it is a horizontal asymptote. The x-axis is another horizontal asymptote on this end. So one horizontal here and one horizontal here. At this end, get closer to this. On this end, get closer and closer to this. So to graph this, so how do you graph this? Okay, so let's try to graph it. Okay, so first we have this negative, okay, before negative 2. Okay, so you see over here, this is negative 2. Okay, right here. But before that, it is concave up and it is increasing, right? So how do you make concave up and increasing? So you do this, right? So concave up and increasing like this. Between negative 2 to 1, remember, to 1 over here, right? The graph is going to be concave down. You see the graph over here? It is concave down. So the graph is concave down and the function is increasing. Okay. So concave down and increasing from negative 2 to 1. So we're going to graph it this way. So you see that from negative 2 to 1, it's going to be increasing and it is concave down. So go like this. Okay. Now from 1 to 2, it is concave down, but the function is going to be decreasing. So you draw like this. And after that, it's going to be, what does it say? It's going to be decreasing and then concave up. So, and remember, this is a horizontal asymptote on this end. So I make it closer and closer to that. So it goes like this. You guys see it? Okay. The last part over here will be the second derivative test. Okay. Now we have the first derivative test, right? Now we have a second derivative test. Okay. So suppose we have this. Okay. Suppose the second derivative is continuous near C, and you know f prime of C is equal to 0. So near this C, because the second derivative is positive. Okay, suppose the second derivative is positive, and f prime is, okay, suppose f prime of C equals 0, and f double prime of C is positive. So near this point, the graph will be concave up. So FC over here will be a local mean. Now, if f prime of C equals 0 here, and f double prime of C is negative, then near this, the graph will be concave down because the second derivative is negative, so concave down. Then the function value here will be a local max. So that's the lowest, that is the highest point, right? So the function value FC is a local max right here. That's called a second derivative test. Now I'm going to try some example with you, okay? Okay, so this example over here. This example over here, we're trying to find local max and mean, okay? I'm going to use two different methods, okay? I compare them side by side, and now you can see, you can compare them, okay? Easy for you guys to see. So I'm going to use the first derivative test and also second derivative test to find local max and mean, okay? Now for both of them, the first step here is to find the domain. So what's the domain for this function? Can anyone tell me?
All real numbers.
All real number. Okay, so all real number. Second step is to find critical number. So we're going to differentiate the function. Differentiate that, what do we get? 4x cubed minus 12x
squared.
You got it. Now we factor this. Okay, so we factor. Okay, we factor this and set the equal to 0. This equals 0 when x equal to what?
0 and
0
3.
and 3. Yeah, so those are the two critical numbers. They're in the domain. It's never going to be undefined, so those are the only critical numbers. Okay. Now I'm going to use the first derivative. So I'm going to use the first derivative test and also second derivative test. Okay. Now let's do the first derivative test first. The first derivative test here, we use a table. So we put the critical number here, and then divide the whole domain, okay, into disjoint interval here. And then we test the sign for the first derivative. So you see the, now I'm going to pick a number here at this interval. Let's pick, say, 10. Substitute over here, I see the derivative is positive. So it's positive, okay? Now over here, what about this? Substitute. Pick a number, say 1 in this interval. So pick a number here in this interval, say 1. Substitute here, we'll get negative. Now what about this? Let's pick negative 1. Substitute here, positive negative. Substitute negative 1 in here, into x. Negative 1 squared is positive 1. Negative 1 minus 3 is negative 4. So it is negative. So it should be negative here. Okay, negative. You see now the sign doesn't alternate, right? The reason is because it's square here. So this is not x to the first power. It's not a linear factor. It's actually second power. Okay. So the square here is going to make the sign here not alternate like before. Okay. So be careful with that. Okay. Because it's square there. Now, first derivative is positive. Then the function is increasing, negative decreasing, and negative here decreasing. Now you see that this is going to be a local mean. The function value here is a local mean. What about this? Local mean or local max or neither?
Neither.
It's neither, right? It keep on decreasing, right? Decreasing on the left and decreasing on the right. So keep on decreasing. So that's neither. Okay, neither. Okay. So that's going to give you the information. So you found this is the only local mean. Okay. So this is neither. What about if I use the second derivative test? The second derivative test says that after you find those c that the first derivative equals 0. First derivative equals 0 when c equal to 0 and 3, right? Okay. And then you will try to see what happened at the second derivative at this 0 and 3. So at 0 over here, second derivative, I'm substituting 0 into the second derivative, into the x in the second derivative. Positive and negative, substitute 0 here. It's neither. It's actually 0. Okay? So substitute 0 into x over here. You get the second derivative is 0, which is not positive and it's not negative. So the second derivative test tells you nothing. Tells you nothing about the f of 0. Okay? Now what about S3? S3, the second derivative, substitute 3 into x over here. We will have positive times positive, so it's positive. Okay? So the second derivative will be positive S3. So near this point, the function will be, the graph will be concave up. So this will be a local one. Then some people will say, when do you use the second derivative test? You use second derivative test when it's easier to take second derivative, and the second derivative is not going to be equal to 0 at those numbers. Then that will be useful. Okay. Now at the end, I also put them together. Okay, I summarize it. Okay, so first derivative test and second derivative test, both of them have this. The first two steps will be the same. Find the domain and take the first derivative. First derivative test over here, you find critical number and you use critical number to make this table, and then you can find local max and local mean. Okay, okay. Now for the second derivative test, then you set the first derivative equal 0, you find those numbers, and then you still need to find the sign of the second derivative at those numbers. If the second derivative is positive at that number, then the graph will be concave up nearby. So that FC here is a local mean. If the second derivative is going to be negative at this C, then near this C, the function will be concave down. Then the graph will be, so f of C here will be a local max, right? So we're done with 4.3. That's the end. So we covered a lot. Well, I went over a little bit. So I'm going to stop here now. Okay. So that's the end of the lesson. Thank you, Alex. Okay. I know, at least I know you guys still here and still pay attention.